Gen exam meeting. Today I want to present a report on generalizing non-local-means to super-resolution reconstruction. For this report, first I will explain what is the problem, then I will talk about the background, the classical method, and also the new method. Then I will talk about the non-local means, and I will talk about the super-resolution method, and finally I will talk about the experimental result, and followed by the conclusion and future works. Super-resolution reconstruction combines several low quality measures into one higher quality result with better optical resolution. This is an inverse problem that combines denoising, developing, and scaling up paths if they want to recover a high quality signals from degraded version of the high resolution one. This picture explains how a low-resolution image segment YT is related to an original higher resolution movie XT. The scene may become blurred due to atmospheric lens or sensor effects, which is shown by edge. And similarly, the loss of spatial resolution due to the sensor array sampling is modeled by the fixed estimation operator as D. And finally, barred Gaussian noise is assumed to be added to the measurements. How do we reserve this reverse this process, or how to get XT from YT? The answer is the super resolution. The super resolution goal is the recovery of XT from the input set of images YT. Webcams, cellular phones, security cameras generate low quality video sequences. It is super resolution duty to reconstruct better resolution for those low quality video sequences. This reconstruction requires highly accurate motion estimation, which classical super resolution cannot handle it. So the question is, can we bypass this limitation? Yes, we can. And in this talk, I will explain a super resolution reconstruction algorithm that relies on motion estimation and quasi motion estimation. As a background, we can say that the general content movies are not likely to be handled well by classical super resolution techniques, because the classic super resolution methods makes many limiting assumptions that are related to the motions in the scene. This is not the case with the quasi motion estimation, which can handle local motion. Also, due to accuracy depends on picking trajectory points, the classical super resolution cannot be used with 100% accuracy on general content movies. So, since the warp operators are hard to obtain in general, super resolution algorithms are typically they cannot handle the global motion characteristics. And another question is there no hope for sequences with general motion? This question will answer with new methods. In contrast of the classical super resolution method, a recent group of methods presents a new technique to avoiding explicit motion estimation, such as non-local-means as an NLM, or adaptive window NLM, sparse representation, and their dictionary. And also, all these methods assume that high degree of redundancy is available in any natural image. I will talk about more of them in the next slides. I begin the method with a description of the bilateral and NLM filters. The bilateral and the NLM filters are two very successful image denoising filters. While not the very best in denoising performance, these methods are because these methods are very simple to understand and implement, and this makes them a good starting point for our needs. Both the bilateral and NLM filters are based on the assumption that image content is likely to repeat itself in some neighborhood. So denoising each pixel is done by averaging all pixels in its neighborhood. However, this averaging is not done in a blind and uniform way. Instead, each of the pixels in the relevant neighborhood is assigned a weight that reflects the probability that this pixel and the pixel to be denoised had the same value. And you can, for example, you can see in this picture that these three patches are similar to the patch P. And this one is the denoising formula. And for example, in this picture, in this formula, the NKL is the neighborhood of the pixel KL, and the WKLIJ is the weight for the IJ's neighbor pixel. And the YIJ is the input pixel, and the X hat KL is the output result in KL. These two filters differ only in the method of computing the weights. The weights for the bilateral filter are computed based on proximity between the pixels, where the weights for the NLM computed based on the Euclidean distance between two image patches centered around these two involved pixels. And the function f in the both weights formula is an non-increasing function like Gaussian, or is as a constant. The penalty function I will start with reflects two forces. First, we desire a proximity between the reconstructed image X and input image Y. And second, we would like each patch in the resulting image to resemble other patches in its neighborhood. However, we don't expect such a fit for every pair, and so we introduce weights here for them. So we can put these two forces together with proper weighting, and we have a maximum a posteriori probability as a math penalty of this form. And I want to note that the path extraction operator R hat KL that are being used in the computing grades, and RKL here they don't have same sizes. Assume the weights are predetermined, so we consider them here as a constant. And we can minimize this penalty term with respect to X by zeroing its derivative. For simplicity, we can open the brackets, and we have this equation. We have this assumption also. Like, as I said, that the weights are predetermined and constant, and also the neighborhood is symmetric. This means that if Ij is the neighborhood of the KL, so KL is in the neighborhood of the Ij. Also, the weights are symmetric. It means that the WKLIJ is same as the WIJKL. Using this assumption, we have these equations. And using these equations, we can simplify the penalty function that we had before, and it becomes like this. So, because these two are same, so these two are same, and these two are same, so we have no half here, and this equation becomes this one. Since solving the previous equation directly is possible in principle and it requires an inversion of a very large matrix, instead we adopt an iterative approach based on the fixed point strategy, with noting xn minus 1 as the output of previous stage, and the xn is desired outcome of current iteration. And we can rewrite the previous equation with this assumption, and we have this equation here. This one leads to this relation. And the matrix multiplying xn, this matrix, is a diagonal positive definite matrix. The only task for this matrix is normalization of the weighted average that took place on the right hand side of this equation. And as this matrix is invertible, the new solution is obtained by this equation. As we will be using the previous equation for one iteration only, and with the initialization of the x0 equal to y, this means that the output for the denoising process is x hat equal to x1, and it obtained by this equation. This process is a more general and more powerful denoising algorithm than NLM, and in order to see how the NLM emerged from this formulation as a special case, we will assume further that the hash extraction here extract only a single pixel in location ij, or here just location of the here just location of the ij. This change means that the Rij is in fact a single pixel of the void of Rij. So the Rij exact single pixel. So we have the Rij is equal to the sorry, it was a y here. Rij y is equal to y Rij, and we have this equation with the using of this property. A natural question to ask is, does this formula still stands for a patch-based algorithm? The answer is yes, because the weights may be computed using patches as the NLM does. And also another question we can ask is, why have we used a patch extraction operation in the definition of our penalty function? The answer is we want that one just for the generalizing that we have in the next slides. But that one is for the super resolution. So we need that one for generalizing for super resolution algorithm. And the result of this one, it should be here for each pixel of the KL from the Rj. Before we turn to super resolution, we must introduce the temporal access into the penalty function. So, as process a sequence of images and not just a single one, some changes in our penalty function need to such this penalty function here. This expression makes use of the input sequence of YT as an input frame and T as a number of frames in the sequence. The term RJYT is the same as before, and this one extracts a 2D patch, but it is a patch that is extracted at location of the IJ from the image at time T. The image X remains a single image representing the desired output image to be created. Assume that the patches extracted by the operator R are size of 1 pixel, and using the same algebraic steps as explained in the previous, we get a closed form formula for the computing of this equation. And in this example, you can see that we add the T here also. And the WKLG, we can add T also here. In classical motion estimation methods, each pixel may be assigned with just one motion vector. As you can see in this slide, for each pixel in X, we have only one pixel in each frame. But in fuzzy motion estimation, we have different strategy. This is a very basic motion estimation approach for each pixel. In fuzzy motion, for each KL, there may be several non-zero values. This implies that each pixel may be assigned with several motion vectors and not just one. So, as you can see, for each pixel, we try to find some motion vectors. It is neighborhood in each frame, and we may find several good matches in the neighborhood for each pixel in the X. Developing a super resolution algorithm will again start with writing a proper penalty term and minimizing it. The input to a super resolution algorithm is the set of low resolution YT, and according to this fact that the target image X and the input image YT are not the same scale, we have to change our penalty term, and these changes are adding D as a decimation operator and B as a blurring operator. And applying these operators on X simulates the imaging process, bringing X to the same resolution as the input YT. And we need to change the order of decimation for realizing super resolution. And RKLDHX equals to the DRKLHX. And also here we have the additional TV as a total valuation expression for the regularized this equation. And you can see here that we have two parts, two states. The first one is the denoising, and the second one is the deblurring state. And since there are two different scales and sizes for the patches, we must differentiate between the patch extraction operator for the low resolution and high resolution. So we define the RKLH to extract the high resolution patch as KL, and RLIJ to extract the low resolution patch as IJ. And the stars are linked through the value of the scaling parameter S, and you can see that the P as a if P if the high resolution patch is the P by P and the low resolution is Q by Q, the P is equal to Q minus 1 divided by S plus 1. And using the changes that I said, we have this boundary function here. And another thing is that we cannot use the neighborhood KL because now the IJ and the KL they are not in the same resolution grid. So we can redefine the NL that the NN is if the IJ is in NNKL, this means that we have the IJ that the SI and SJ is in NKL, the neighborhood of the KL. Our process can be divided into two stages, as I said, denoising and debilitating. The idea of the breaking the super-resolution task into two parts is not new and has been suggested previously in several works. Also, using the substitution z equal to hx, it means that this one as the first problem we have is the estimation of z from the measurement of the yt, which is done by minimizing this energy function. When we found the z, we can use the found z hat to estimate the x by minimizing this equation. The first part can be done as I explained in the previous slide. And the second part is a classical simple debilitating problem, and we can use any state-of-the-art debilitating methods here for debilitating the z and find x. So the high resolution image x is the result of the super resolution algorithm that I explained. And here is some result from the paper. For all the three sequences they tested on their paper are America, Foreman, and Suzy sequences. For all the tests in this paper, an input sequence is prepared using the 3x3 uniform task, and is measured by a factor of the 1 to 3, and the additive noise with the standard deviation of the 2. Also, all images are in the input range of the 0 to 255. And also, as there is no published methods that perform super resolution on these sequences, they just compare the result with a single image of sampling using sampling that is the image is the dark source interpolation. And you can see here that this one is the input sequence at a low resolution, and this one is exactly they degraded the original sequence, and they applied their method and also the dark source method on this low resolution, and found this one for the dark source, and this one is the result of the result. And also here is for the Foreman result, and also they use the 30 frames for the low resolution and apply the work and the long source integration on that one. And this one is the result also. And also we have the Suzy sequence and the result of the Suzy. The results obtained are very encouraging and being high quality, but still in their paper they believe that these results could be further improved and extended in various ways. And as I said, that this paper introduced a novel super-resolution algorithm which doesn't rely on the explicit motion estimation. And for the future works, they discuss some of them in their paper. For example, the manual selection of the various parameters, they said that it could be replaced by an adaptive setting of their values. For example, one specific parameter of importance is the filtering parameter, sigma in the weight, which is affecting the weight computation. And selecting this parameter in a locally adaptive way seems like a natural step to take, and allowing the algorithm to adapt better to both small and large details. And another thing is that an adaptive selection of the window size can improve the algorithm performance also. The window size, the bit size for the both weight and computation, weight computation, and also in the algorithm itself. And similarly, while the estimated motion pattern is fuzzy, reducing the number of candidate locations can help reduce the complexity and can improve the results. Any